that's why we study antimatter. Well, I mean, that's one of the reasons why. The other reason is that it's cool. But if we learn about antimatter, we can learn about the start of our universe. We can learn about cosmology. Because what if we did make an anti-helium, you know, two anti-protons, two anti-neutrons, and two anti-electrons, and it didn't behave like a helium? What if it was like a little bit different? That difference could help explain the symmetry breaking at the start of the universe. It could explain why matter won over antimatter. I was talking about the hydrogen atom the other day, and I was like, look at these energy levels. When you have an electron at this energy level, it wants to go back down, and it emits a photon of a very specific wavelength. And you can look at the spectra of those photons and know exactly what molecule we're looking at. Anti-hydrogen should have the exact same energy levels, so we could make an anti-hydrogen. And what if, instead of having a binding energy of minus 13.6 eV, the anti-hydrogen had a binding energy of minus 13.41 eV? Wouldn't that be crazy? Then we could learn about cosmology. Finally, we would have answers, but it turns out like it behaves exactly the same, which is kind of what we predicted with quantum mechanics. So, but it would be cool if it didn't. What if you made an anti-carbon and the bonds were stronger or something, and you could be like, the aliens will be anti-carbon. So we know that most of the antimatter is gone, but antimatter is still made in normal everyday interactions the same way matter is still made in normal everyday interactions. One of the ways is through cosmic rays, just like interacting with the atmosphere. You can make it an electron and an anti-electron. You can see those in your detectors. Another way is through radioactive decay. So things like potassium have these decay channels that will produce antimatter. Your body produces antimatter every day all the time. The bananas on your counter, you've heard that bananas are radioactive, right? They have a bunch of potassium. One version of potassium is radioactive. It just emits a bunch of radiation, and some of that is antimatter. Neat. But physicists want to study antimatter, of course, to learn about cosmology and all that other stuff, also because it's cool. And because of that, we want to make antimatter. We want to make stuff that's bigger than like an anti-electron. And to do that, you need particle accelerators. Because in collisions, as I've been hinting at this whole time, you make pair production. If you make a proton, you have to make an antiproton. So what if you did that a bunch of times? You got a big old stockpile of antiprotons. And antiprotons are just anti-hydrogen ions. And then you've got an anti-hydrogen ion gas, and you could study it. Wouldn't that be cool? So let's talk about CERN. I don't know why I always say CERN. There are so many different accelerators. Is CERN just the most famous one? Alright. So I think I mentioned earlier that you can do pair production as a result of collisions. Like if you throw particles together, a bunch of crap comes out, and you can study that crap to learn about the world. So if you take two protons and you slam them together, one of the interactions results in pion production. And the pion is a subatomic particle that's like two quarks bound together. They're relatively low mass. The mass of the proton is 938 MeV, and a neutral pion has a mass of 135 MeV, while a charged pion has a mass of 140 MeV. So these are relatively low mass comparatively. So these reactions are like proton plus proton yields proton plus pion. So the way these guys work is you have like a stationary target, and if you want to do a proton-proton collision, your target has to be made of protons. Usually you just have like a stationary hydrogen gas. So like you don't care about electrons. Like electrons are garbage. They're so small. Your proton's huge. It's going to slam into another huge proton. The electrons don't even matter. So that's stationary. And if you want something to come out of this collision, you have to give energy to your proton beam that's going to slam into these stationary protons. So you might think like, okay, if proton plus proton yields proton plus pion, you just have to give that beam of protons 135 MeV. You give it enough energy to flip it into this other stationary proton, and they'll stop, and out comes your pion. But no, not actually. Have I mentioned that conservation rules all? You have to have momentum conservation. So if this guy is stationary, but you're slamming a moving beam of protons into it, there's momentum in this interaction, which means there has to be momentum after. So you have to give your proton beam much more than 135 MeV to get a 135 MeV particle out. Let's do the math. So let's go to the lab frame where you have a proton beam moving with some velocity v, and it's going to slam into a proton that is stationary. This is our initial condition, and there is momentum here, right? You have the mass of the proton times the velocity of the proton. So imagine you gave this proton that's moving 135 MeV. So that's its kinetic energy. It's going to slam into the stationary proton, and you want all of that kinetic energy to be turned into a pion. So your end result would be 2 protons and then your pi 0 just hanging out. Except this doesn't conserve momentum, right? Because you have momentum here. If all of these are stationary, if every bit of that kinetic energy got turned into this mass, you have no momentum. That breaks conservation, which is the biggest rule in the universe. You have to conserve everything all the time. So instead, you need to give this moving proton more energy. It has to have more than 135 MeV. Let's calculate how much that is. Okay, so let's go to the center of mass frame, where your proton is moving this way, and the proton that was stationary is moving this way. Okay? Here, in this situation, momentum is 0 because you have an equal velocity going both ways. They cancel out, which means after, our momentum can also be 0. So now let's look at conservation of energy. If at the end of this we produce a pion in addition to our 2 protons, this whole situation will have some energy, and it has to be equal to whatever the energy was over here. So when we're looking at our initial energy, we're going to have to account for the relativistic Lorentz factor. And on the right-hand side, after this collision, we're just going to have the rest energies of the particles. So that's going to be 2 mp c squared plus pi c squared. Let me just plug in gamma. So mp c squared over 1 minus v squared over c squared. All of these are known values. Like, we know the mass of the proton, we know the mass of our pion, we know what C is. What we can do is solve for V in the center of mass frame, and what we get is that is equal to 0.36 C, which is very fast. But we need the velocity in the lab frame, right? Because remember, we're shooting a beam of protons at stationary protons. So the proton that's moving is going to have 2 times v center of mass. And when you're adding relativistic velocities, you can't just say 0.36 plus 0.36. You have to do the special relativity formula. So let's do that. So v lab is going to be equal to v plus u over 1 plus du over c squared. Here v and u are equal to 0.36, so when you work this out, you get that v in the lab frame is 0.64 c. So if you want to make a pi 0 in your collision, your initial proton has to be traveling at 0.64 c, which is why they make these giant accelerators. You have to get these protons up to relativistic speeds in order to start making stuff. And I think it's easier to think about this in terms of energy. So the energy of that initial proton is going to have to be gamma minus 1. We know this is 938 MeV. So the energy that you're adding into the proton is going to be 280 MeV. What this means is, in order to make a particle that has a mass of 140 MeV, you need to put at least 280, probably more than that, 290 MeV into your proton. So This is called the threshold energy. You have to add enough energy to conserve momentum in order to make the mass. So if you're making a very tiny particle, you have to put double the amount of energy into your proton in order to get that particle out. This is super inefficient. You have to double the energy you add to the proton beam in order to make these teeny tiny particles. But they're not in it for like efficiency. They're not trying to conserve energy here. They're trying to study those particles. So you have to do that the only way you know how is to make them in an accelerator. But what if you want to make antimatter? What if instead you want your proton-proton collision to produce a proton-antiproton pair? You have to put a lot more energy in. Instead of doing the proton plus proton yields proton plus proton plus pi zero, you want the proton plus proton yields proton plus a proton antiproton pair.